Welcome back. Today we're doing section 3.5 on inequalities with integers. Pardon me. So if we're restricting ourselves to the integer domain, which we're in chapter 3 still, so we are, starting on 4, we're going to expand to more number sets. Then our answers are going to look a little bit different than if we had all the real numbers to play with as our domain. So we'll start with how to show a solution of x is strictly greater than 5 as the solution if our domain is still the integers. And I'm going to start with the graph, and we will also write a solution set. So I'll just start with a quick number line here. So here is our 0 in the middle. So this is basically working with the x-axis only. So here's our 0 in the middle. We want x to be strictly greater than 5. So here I'll just count up by ones. Here's 1, 2, 3, 4, 5, 6, 7, etc. And -1, -2, -3, etc. that way. So notice 5 itself does not work. 5 is not bigger than 5. 5 is the same as 5. So here is where we're sort of splitting the number line into two pieces. And you can just kind of pick a number on either side and see which side makes sense to keep. 0 is greater than 5 is also incorrect. So we don't want the side with the 0. If I picked a number over here, say 7, 7 is greater than 5 makes sense. So we want the numbers this time to the right side of the 5. So I want the 6, the 7, the 8. And to show the reader that we keep going on the integers only, we do an ellipsis up and in this case to the right since we're going to the right-hand side. This is sort of a unique notation when you're working with an integer domain only. As far as our solution set, we have to keep the 6, 7, 8, 9, and we got to keep going forever, so we have an ellipsis in our solution set as well. So it's two ways we would express that solution. Next up, we'll look at 2 is greater than or equal to x. And again, I'll start with a graph and then do a solution set after I've made the picture. So here's my 0 in the middle. And again, I'll just mark it every quarter inch. Okay, so there's our x-axis again. Our 0 in the middle, we don't need to scale it at all. Counting by ones is sufficient here. Okay, so here this time 2 is the number that's sort of in the hot seat. It's cutting up this number line into this side versus that side. So again, I'll just pick one guinea pig on either side and see if it makes sense when I plug it in. 2 is greater than or equal to 0 is true, so this means I probably want the side with the 0. If I try something from over here, it's going to give me a false statement. So for example, 2 is greater than or equal to 6 is not true. So I want the side with the 0. This time I can include the endpoint of 2 because of this or equals line underneath. 2 is greater than or equal to 2. So I want this time all the numbers traveling in this direction. And since I'm traveling in this direction forever, I end it with an ellipsis up and to the left this time. That informs me of what my set notation will look like. So our solution set, we're coming from negative infinity. So then we have, I just need to list maybe 4 numbers in the set to show the pattern. So we'll just go -1, 0, 1, and 2, and that gives the reader enough information to form the pattern that we're doing integers ending at 2. So then we get into some of the properties of integers. So we're going to just pick out a couple random numbers. Let's see. All right, one book I have is open to page 113. One book is open to page 48. If I were to make this into an inequality, we'll use the strict inequality. We could do the same thing with an or equals involved. 113, I think we can agree, is bigger than 48. If I pick a number to add to that, let's say a 6. I do 113 plus 6 and 48 plus 6. So 119 versus 54. My inequality symbol hasn't changed. 119 is still bigger than 54. If I subtract something from both sides, let's say 9. So we have 110 on the left-hand side and 45 on the right-hand side. 110 is still bigger than 45. So adding and subtracting positives didn't change the inequality symbol. Next, we'll add a negative. Let's say a -5. So 105 on the left-hand side, 40 on the right-hand side. Still no change in the inequality symbols. Okay, next we'll subtract a negative. We'll subtract a -5. Well, remember, subtracting a negative is the same as adding a positive. So right back at our 110 and our 45. So adding a positive, adding a negative, subtracting a positive, subtracting a negative, none of that moved the inequality symbol around at all. We can summarize that. If A is greater than B, then A plus C has to still be greater than B plus C. In other words, we can add or subtract anything we want. Remember, subtracting is just adding the opposite. So this still holds for A minus C being greater than B minus C. So next we'll look at multiplying and dividing. We'll do some smaller numbers this time. We'll do, I don't know, 8 and 12. Okay, so this one I start with a less than. We'll multiply both sides by a positive 2. So 16 and 24. 16 is still less than 24, so the inequality symbol didn't move. Now we'll multiply both sides by, let's say, a -3. So -48 on the left-hand side, -72 on the right-hand side. Now you want to be careful here. Think of these as dollars. You're in less trouble if you're overdrawn by $48 than if you're overdrawn by $72. So -48 is actually greater than -72. So this is the first time that we've flipped the inequality symbol around from what it started as, multiplying both sides by a negative. Let's do a little bit of work with division then. Let's see, so we'll do -48 divided by, well, let's say by -2. And -72 divided by -2 as well. Negative divided by negative is a positive, half of 48, 24. Negative or negative is a positive, half of 72, 36. 24 is smaller than 36. Flip from being a greater than statement to a less than statement. So it looks like multiplying by a negative flipped it, dividing by a negative flipped it, dividing by a positive, however, well, let's use just 12. Get a 2 and a 3. That stays where it is. It was a less than before. It's still a less than statement. So our statement for multiplying and dividing is actually more complicated than for adding and subtracting. So we'll start with if A is, well, let's say less than B. And C is greater than 0. Greater than 0, remember, is implying positive. Then AC is still less than BC. In other words, the inequality won't move if you multiply both sides by a positive or divide both sides by a positive, since division is multiplication by a reciprocal. Part 2, though, says if A is less than B and C is less than 0, in other words, C is negative, then our inequality symbol has to flip. AC would be bigger than BC, or A over C would be bigger than B over C. In other words, multiply or divide both sides by a negative, you have to flip your inequality sign. So other than that, all of the properties do hold that we've worked with in Chapter 2. All the properties of multiplicative inverse, additive inverse, all that other fun stuff. All right, so if they ask us to solve one of these, we'll start with a short one. X minus 8 is strictly greater than a positive 4. We're going to do subtraction with addition. And as long as I'm adding or subtracting, the inequality symbol is brought down exactly how it was. So x is greater than 12. So we'll do our graph and we'll do our solution set. And this time, notice I'm all the way over at 12, so instead of putting the 0 in the middle, we'll put the 12 in the middle, and we'll just look at both sides then. So 11, 10, 9, 8, 7, 6, 5 on that side, and it keeps going forever that way. 13, 14, 15, 16, 17, 18 on that side, keeps going forever that way. Okay. So the 12 is our border. So we take a guinea pig from either side and see who works. 8 is greater than 12, doesn't make sense. 15 is greater than 12, does make sense, so I want the right-hand side. 12 is not greater than 12, so I don't get to keep that point. So I'll keep 13, 14, 15, 16, 17, 18. And to tell the reader that I can keep going as high as I want to go, the ellipsis up here in the corner. So if they want the graph, that's what our graph looks like. If they want a solution set, our solution set starts at 13. So 13, 14, 15, 16, that's enough to show the pattern. So then we do our ellipsis. Okay, our next problem, we're asked to solve the inequality 5 and 9/10 is strictly greater than the sum of x and 11. So I'm looking to get the x by itself, so I'll subtract 11 on both sides. Adding and subtracting will not affect the inequality symbol. That stays parked. So notice I did the same thing on both sides of the inequality. So unlike signs, so we'll subtract those absolute values. If it helps you think of it as 11.0, that's fine. So 10 minus 9 is 1, and 10 minus 5 is 5. So 5 and 1/10 is greater than x plus 0 will turn into an x. Remember our domain, though. Our domain is the set of integers, not the set of real numbers at the moment. So we'll get our graph going here. And just a little dash every 1/4 inch. Sure do miss that graph paper that's sitting in my desk at work. All right. I'm not going to put 5 and 1/10 as my point. The reason being, one, generally number lines don't start at a number that is 1/10 of a unit away from an integer. So we'll start with a 5 in the middle. So 6, 7, 8, 9, 10, 11 this way. And 4, 3, 2, 1, 0, -1, -2 that way. So 5 and 1/10 is between the 5 and the 6. So that's sort of our border. We're between the 5 and the 6. So again, we'll just sort of use a guinea pig from each side and see which makes sense. 5 and 1/10 is greater than 0. Okay, that sentence made sense to me, so I'm thinking it's the left side. I'll just make sure with something from the right side. 5 and 1/10 is bigger than 10. Doesn't make sense. So we want the left side. So 5 is to the left of 5 and 1/10. So it's 4, 3, 2, 1, 0, -1, -2, and so on forever this way. So we show the ellipsis up and to the left of the number line. So there's our graph. Our solution set, coming from the left, we were approaching -infinity. And then again, just 4 numbers, so we'll make sure we can show the pattern. So 2, 3, 4, and 5. So notice I'm not including the 5 and 1/10. Would that be different if I had an or equals under each of these? In this case, no. 5 and 1/10 is still not in the set of integers, so I still wouldn't have gotten to keep it, even if, I'll do the what if, even if they had been greater than or equal to symbols included in the problem originally. All right. So next up, x11s is at least 5. Again, we're going to assume they're telling us to solve like they did in the last problem. So we'll undo division by 11, multiplying both sides by 11. When you multiply, take a second and think, am I multiplying by a positive or negative on both sides? We were multiplying by a positive on both sides. That will not change our inequality symbol. So I will bring this straight down again as a greater than or equal to symbol. Left side 1 times x is x. Right side 11 by 5, 55. So again, we'll do our graph and our solution set from there. Okay, so I'll put my 55 in the middle and we'll just count by ones. Okay, so our border is the 55, so I'll just take a guinea pig from each side, see which one works. 48 is greater than or equal to 55. That doesn't make sense to me. But 61 is greater than or equal to 55 is true. So I want the right-hand side. And this time with the or equals, and since 55 is an integer, I will keep the 55. And again, our ellipsis this time up and to the right. So our solution set starts at 55. So 55, 56, 57, 58. And we can go forever, this time in the positive direction. Okay, so next up we'll do 35. If you remember, I'm currently quarantined with my 8-month-old and my wife, so you may occasionally hear her in the background. Let's see, 35 is strictly less than a negative 5 times x. Okay, we're looking to solve that. So I want the x by itself. It looks like I'm going to be dividing both sides by a negative 5, and that's when the alarm bells start clanging in your mind. If you are dividing both sides by a negative, you have to flip the inequality symbol around. We divided both sides by negative 5, multiply or divide both sides by a negative, flip that inequality symbol. After that, it's all just simplifying. So negative 7 is strictly greater than x. So then we're just ready to get our number line going here. All right. So we'll put our negative 7 in here. You want to be careful when you're on this side of the number line. Remember, we start with 0 in the middle, 1 and negative. 0 in the middle, 1, then negative 1, 2, then negative 2, 3, then negative 3. In other words, as we go to the right, we're dropping an absolute value when we're on the negative side. We're getting closer to the positive numbers. So just watch that you don't flip that those numbers around onto the other side. So again, just one sort of guinea pig test point from either side. From the left side, negative 13, negative 7 is greater than negative 13. That is true. You're better off with being overdrawn by $7 than being overdrawn by $13. And a number over here would be false. And it doesn't have to be one of the ones you can see. You can go really far to the right. You can test out positive 500. Negative 7 is bigger than positive 500? No way. So we didn't want the stuff on the right. We did want the stuff on the left. Strict inequality, so I'm not allowed to use that negative 7. So I'll have to skip, since we're doing integers only, I'll go to the negative 8. And the ellipsis up and to the left, since I'm going left forever. So there's our graph. So our set, we're coming in from the negative infinity direction, and just the first maybe 4 points there, negative 11, negative 10, negative 9, negative 8. Even though we saw the negative 7, we're not allowed to use the negative 7. Negative 7 is not bigger than negative 7, so that is not going to be a true statement. So this was the key feature of that problem. If you multiply or divide both sides by a negative, make sure you flip that inequality symbol. And occasionally we'll do multi-step problems as well. Let's see, we'll do maybe a negative 3x plus 11 is less than or equal to 2x plus 3. So first things first that I notice on this one, I don't have the x's on one side. So I can either add 3x to both sides or subtract 2x on both sides. From what I remember in class, I think more of you would have preferred the addition over subtraction, so we'll add 3x to both sides. We'll get the same answer either way. Add or subtract all you want, the inequality symbol doesn't budge. 0 plus 11 is just 11 on that left-hand side. 3x and 2x is a 5x, 5x plus 3 on the right side. So next up, I'll subtract 3 on both sides. Add or subtract all you want. Inequality symbol will not move. So 8 is less than or equal to 5x. We'll finish off dividing both sides by 5. I divided, but it was by a positive 5. The inequality symbol is okay where it is then. Stays a less than or equal to, so 1 3/5 is less than or equal to x. So now we can do our quick sketch. And our solution set. Okay, 1 3/5, that's between 1 and 2, so I'll just put 1 and 2 in the middle here. So here's 0, negative 1, negative 2, negative 3, etc. going that way. 3, 4, 5, 6, 7, 8, etc. going that way. Okay, 1 3/5, that's between the 1 and the 2. We'll take 1 from each side and see if it works. 1 3/5 is less than or equal to 0. Positive less than or equal to 0 doesn't make sense. So I'm thinking that everything over here will work. 1 3/5 is less than or equal to 8 is true. So I want the stuff on the right-hand side. I can't keep 1 3/5. That's not an integer, but 2 is on that side, and I can keep that. So I'll start at 2 and work our way up on the integers. So the ellipsis up and to the right. So our solution set for this one, 2, 3, 4, 5, and then our ellipsis after that last comma. All right, just a couple more, and then we'll pause on the 5-1 stuff. All right, so let's see. So we'll do a negative 5 by the quantity x plus 2 is less than or equal to 3x plus 2. Okay, so on this one, I notice I do have some simplifying to do. So I'll use the distributive property. So negative 5x minus 10 on the other side of 3x plus 2. Now, here's where the controversy starts. What do I do with that inequality symbol in the middle? I multiplied by a negative, that's true, but I didn't multiply both sides by a negative. All I did was simplify on the left side. That inequality stays put. If I multiplied both sides by -5, I would have to flip the inequality. But if it's just one side, I do not flip the inequality symbol. So after that, solving as usual, get your x's on the one side. Let's see, we did the other one, the last one the other way, so this time I'll subtract 3x on both sides. Add or subtract all you want. Inequality symbol stays put, so -8x minus 10 is less than or equal to +2. Add 2 to both sides, or I'm sorry, 10 to both sides. So -8x is less than or equal to +12. Divide both sides by negative, and there's those alarm bells sounding in your head. Dividing both sides by a negative, that is when we have to flip that inequality symbol around from wherever it was before. So x is greater than or equal to -1, and let's see, it'll go into 12 once with 4 left over. 4 aces 1/2, so -1.5. Really finding her voice today. All right. A lot of fun. Very happy with my quarantine partners, my roommates, my wife and 8-month-old. All right. So we set up our fun little number line here. -1.5, so that's somewhere between -2 and a -1, and then we'll just count on the integers in both directions. Okay, so -1.5, we're between -2 and -1. Again, just test points on either side. So -9 greater than or equal to -1.5. That is not true. But +5 greater than or equal to negative anything is true. So we want the stuff on the right-hand side. So we want the -1, we want the 0, the 1, the 2, the 3, etc. And forever in this direction. And that also gives us a good idea of what our set will look like. -1, 0, 1, 2, and forever to the right. Okay, this is a bigger section, so we're going to sort of hit pause there. And on the homework, you're going to do the single inequalities only. So for now, skip any of the and or problems at the end. So single inequality only in section 3.5. For now. Okay, so give those a try. If you have any questions, please feel free to get in touch with me. Thank you.